Let us next see some examples. Examples of functions which may be 1 to 1 or 2 or not, any combination of these two. So in this first one, let A be the set of all 50 students of class 10 in a school. And then there is this function f whose domain is A, and f maps A into n. N is the set of all natural numbers, that means positive integers. And the rule for the function is this. F is defined by this rule. F of x is equal to the roll number of the student x. You understand that A is the set of all students in the class. So any input x that you take from A will be a student, and f of x is the roll number that the student x is assigned by the school. We have to prove that this function f is 1, 1 but not onto. So let's see the solution. So here's the solution. In the beginning of the solution, we say that we assume that the 50 students are assigned these roll numbers, starting from 1 and then consecutively we reach 50. Okay, so because that's what we do. We do not start the roll number from 2 unless someone who joined the school left the school for something. Then the roll number 1 is gone, or it may be reassigned to someone else, but in a normal situation it starts from 1 and then it goes like that. So here's the point. Since two different students are always assigned different roll numbers, obviously two different students won't be assigned the same roll number, or say more than two students also won't be assigned the same roll number. That is why the function f is 1, 1. Why? Because what is f? The inputs in f are the students and the outputs are roll numbers. So if we take different inputs, the x1 and x2 are two different students, then they are getting different roll numbers. So if x1 is not equal to x2, then f of x1 is also not equal to f of x2, because these f values are roll numbers. That is why by the definition of one-to-one-ness, f is 1 to 1 or 1, 1. But recall that f is a mapping from A into n, the set of positive integers, and you take this positive integer 51. This is not the image of any element of A. 51 cannot possibly be the roll number of any student, and that is why f is not onto. Instead of 51, you can take some larger number also, say 52. Okay, so that can also be used to show that f is not onto. So that's the thing. Let's see the next one. So in this next example also the function has the same nature. We have to prove that it is 1, 1 but not onto. The function is different. This time the function is from the set of positive integers to itself, from the set of natural numbers to itself, and the rule is this. If the input is x, then the output is its double, 2x. So let's solve this. So this is the solution. We begin by taking two natural numbers x1 and x2 whose f images are equal. F of x1 is equal to f of x2. F of x1 is 2x1 and f of x2 is 2x2, which implies, after cancelling 2 from both sides, this, that x1 is equal to x2. That means if we have this, that is if outputs are equal, then inputs are also equal. So that is why our function f is 1, 1. Instead of going like this, you can also go like this. You may remember in the previous video we said that there are two equivalent applications that can be, any one of them can be used to prove one-to-one-ness. So in this other method, what you do, you take distinct inputs. Here you took equal outputs, here you take distinct inputs. Then their doubles are also distinct, because otherwise if these two are equal, then just like that one, you would get x1 equal to x2, which would contradict your starting point. So here if distinct inputs are taken, then outputs are also distinct. So instead of doing this, you can do this also. It's up to you to choose which one you want to choose. Note one more thing, that this is what we did in the previous example. We took distinct students and their roll numbers turned out to be distinct, which is true, which is always the case, and that is why that F was 1, 1. Next we see how it is not onto. So lack of ontoness can be shown like this. It starts from the observation that all the outputs, all the F images of natural numbers are even integers, because f of n is 2n. That is why no odd integer will appear as the image of anything under f. In particular, there is no integer n, no positive integer of course, for which 1 is equal to f of n. In place of this odd 1, you can take 3 or 5 or anything. You just need to show that there is something in that second n, this side n, because f maps n into n. No, from this n, you have to show that there is at least one thing which is not the image of anything under f from that n. So this is one such non-image, and that is why f is not onto. Next, in this next one, it's almost like the previous one, but there is one difference. In place of the set of natural numbers, here we have the set of real numbers, and the nature of the function also changes. This time it's 1, 1, the previous one was also 1, 1, but here now we have ontoness. It is 1, 1 as well as onto, so it's the bijective function. So let's show this. Here's the solution showing that f is 1, 1 is exactly like the previous one. So we again take 2 points, but this time real numbers. Okay, not necessarily, they may be natural numbers, but in general they are real numbers. They may be irrational also, such that their f images are equal. Then by the definition of f, 2x1 is equal to 2x2, which implies that x1 is equal to x2, and that is why our function is 1, 1. But the ontoness, previously we did not have that. You will realize why. Now we take any y in R, thus second R. Second R means this one. For that y, there exists this y divided by 2 in R. In this first R, whose f image is that y, that chosen y, because 2 times y over 2 is y. Why did we not have this in the previous example? That is because for any natural number n, n divided by 2 is not always a natural number, and particularly it is not when n is odd. That is why. Here however we do not have that problem, and so we have ontoness as well. Next. In this next example, we again have a function f from the set of natural numbers to itself, and this is how the function is defined. The rule is that f of n is 1 if the input n is either 1 or 2, and otherwise if n is greater than 2, then the output is n minus 1. We have to prove that this f is onto but not 1, 1. Now looking at this rule for f, it at once seems very complicated. So let us draw a small figure and see what's going on behind these symbols. This figure is actually nothing but the arrow diagram for this function f. Instead of drawing the sets vertically like this, and instead of running the arrows horizontally, I have written the elements of the sets horizontally and the arrows run like this. So let's now see how the arrow diagram comes from this rule. If the input is 1, then the output is 1. So 1 gets mapped onto 1. If the input is 2, then also the output is 1. Otherwise, if the input is greater than 2, say 3 or 4 or 5 or some such number, then the output is 1 less than the input. If the input is 3, output is 2. If it's 4, then 3. If 5, then 4. And from 6, we will get 5. So that's how the function looks. And from this look, you can immediately see that it is actually onto. Why? Because every element in the second n is coming from somewhere, is the image of something under the function from the first set. And also it's not 1 to 1, 1, 1 because of this. It is 2 to 1. So do you see how easy it has become? Simply because we drew this figure. And this figure actually will give us the idea of writing a solution. What will you do now to show that the function is not 1 to 1? You just mention that we have this, that is why it's not 1 to 1. And for ontoness, what will you do? You will take any element from this set n, that any element obviously will be any element from here. If that element is 1, then from where is it coming? You can either mention that it's coming from 1 or from 2. But if that element is something other than 1, say 2 or 3 or 4, then from where is it coming? It is coming from that natural number which is 1 more than it. If it's 4, then it's coming from 5. So you have got the solution almost. You just have to write the things. So let us write the things and see how it looks. So we start the solution with lack of one-to-oneness. F is not 1, 1 because f of 1 and f of 2 are both equal to 1, although 1 and 2 are different. And next we go for ontoness. So we take any n, in n means in this other n, the second n. It does not really matter, there is no first n or second n, I am just simply saying for our discussion. If n is 1, then n is equal to f of 1. N is coming from 1. So n is the image under f of the element 1. So now let n be greater than or equal to 2. So that means now n is some number here. Because n is greater than or equal to 2, n plus 1 is a natural number which is greater than 2. Even when n takes the value 2, n plus 1 is 3, that is the smallest n plus 1 can be. Even then it's greater than 2. So if we now calculate the f value of n plus 1, by the definition of our f, if the input is greater than 2, then the output is 1 less than the input, that is n plus 1 minus 1. So that's how we get n. So in this case also, n appears as the f image of something, and that something is n plus 1, and that is why f is onto. There are other examples and other things after this, so that we will see next week on the same day. So see you next week with those things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.